on with gases? What?
Should have canceled the ICA game tomorrow.
What game did they cancel?
The ICA game.
They canceled it tomorrow?
They should have canceled it tomorrow.
Oh, so you could still be wearing sweatpants? Nice.
Wow.
Why
Okay.
not?
I don't know. ICA can't get 5 people in the court? I don't know.
There's someone that can get beat up.
Probably. That'd be worse.
Doesn't matter, it just ends up as a loss.
Okay, so if I have H2O and I break down H2O into that guy, okay, we know that if I were to break down a mole of H2O, I would get 16 grams of oxygen and 2.02 grams of hydrogen. That shouldn't be strange to you, is it?
No.
No, it shouldn't be, because that's the molar mass, correct? 16 plus 2.02 gives you 18.02, which is the molar mass of water. So it shouldn't surprise you that when you break or decompose a mole of it, that's what you would get for a mass. But here's what's interesting, okay? When you collect the gases, measuring them separately, what you find is that hydrogen has twice the volume as oxygen does. So let me restate this. When you decompose water into hydrogen gas and oxygen gas, you get 8 times the mass of oxygen. But when you measure the volume of the gas, you get 2 times the gas volume of hydrogen. So even though oxygen gives you more mass, hydrogen gives you twice as much volume as oxygen does. Why is that?
It's more,
It's more energy.
yeah.
Since
The gas.
the nucleus is smaller, it doesn't hold on to its electrons as much, so it takes up electrons. I don't know.
The gas. Okay, so we're talking about, let me say that again. A mole of gas breaks up into 16 grams of oxygen and 2 grams of hydrogen, but when you measure the volume of the gas, you have twice the volume of hydrogen as you do oxygen. Up front, that kind of doesn't make sense. Would you agree with that? So there must be an explanation here. First off, it all lies in what a mole is. What is a mole? A number. Okay, what is that number?
6.02.
Okay? So, try to balance that guy. If I break apart a mole of water, okay, how many moles? Let's go 2 moles just so it agrees with the ratios up there. Let's say I break 2 moles down, 2 moles of H2O. How many moles of H2 am I going to get? Not a hard question, guys. 2. And if I break 2 moles of H2O down, how many moles of oxygen gas am I going to get? 1. Okay? So the answer lies in the moles. So when I take and decompose this, I get more. When I say I've got 2 moles of O2 and 1 mole, or 2 moles of H2 and 1 mole of O2, what is that really telling me? What does that mean? Come on.
You got a lot. All in all,
You don't know what that means? You don't know when I say I got 2 moles, if I said I had 2 moles of oranges and 2 moles of apples, you couldn't tell me what that means?
You got 6.022 times 10
Times 2 hydrogen.
and then
Okay. I have twice as many particles of hydrogen gas. Does that make sense? Okay? Well, what do we know about gases from a Well, just tell me what you know about gases. Go ahead. Shout out some things.
Fluid.
Fluid, okay?
Got it.
Has a lot of energy, okay?
Easily compressible.
Easily compressible. And why is it easily compressible?
The space in between the particles is greater.
Ah, the space in between the particles is much greater than their mass. What else? Anything else?
Gases do not interact with each other.
Okay.
Their collisions are
Okay. All good things. Any of those things would help you maybe understand why you get twice the volume of H2 as you do oxygen, even though oxygen has more mass? Any of those things?
Well,
The fact that
there's
the
2 moles of
particles
hydrogen.
Ah, I heard it.
The fact that the particles are spread out.
Yes. Okay, so if a gas molecule has to travel 20,000 times its own radius, or its own diameter, to get to another gas particle, does the volume of the particle itself really take up much of the total volume of the gas? Very little. In fact, pretty much nothing. Does that make sense? So if I have twice as many particles of oxygen gas, I should in theory have twice as much volume. Even though technically an oxygen molecule is a little bit bigger than a hydrogen molecule. But if you throw in the fact that most of a gas is simply what? Open space, does that now start to make a little bit more sense? Okay? So what you have is twice as many hydrogen molecules, and if the volume that they have is solely dependent upon the fact that gases are extremely far apart, the more particles, the more volume. Does that make sense? Okay? So what we can have is this occupies 2 liters and this only occupies 1 liter, even though this has 16 grams and this only has 2 grams. Because of the fact that gases are mostly made up of open space. And this where this comes in, the law of combining volume. Under equivalent conditions, this is pretty important, okay, because you got to keep constants here. The volume of reacting gases of their their gaseous products are expressed in ratios of small whole numbers. If I could just explain that in a more detailed way, or a more simpler way, I should probably say, how I would explain this would be the ratio of the mole coefficients is going to be equivalent to the ratio of your volume. So if I have twice the amount of moles, that gas is going to occupy twice the volume. Or if I have 4 times the amount of gas moles, it's going to occupy 4 times the volume. So, if I've got something as simple as this, if I knew that produced 2 liters of that gas, how many liters of the reactants would I have had to have?
I don't know if we can do that because you
Oh, yeah, I did. Oh, man.
Yeah.
Thank you.
I have 2 liters of each one.
You can have 2 liters each one?
That's wow. Yeah. It's actually really.
You can have 1 liter, because the relationship between the coefficients is the same relationship between the volume that they occupy. Which led a guy by the name of Avogadro to come up with his law. And you don't have to put this one into your chart because we're not going to use it a ton, but this is essentially what his law is. You don't have to, this is not going in your law table, okay?
And is
You don't need to know it, yeah, but it's going to be the least used one. We're actually going to use this, which comes from that. some sense of this. What's the relationship, and what does this make sense to you? What is N? Did I tell you what N? Have I told you? Okay, N is moles. Okay, so what's the relationship between moles and volume if every other condition is held constant?
Go up together.
Go up together or down together, directly related. Okay? So just imagine, if you maintain the pressure and you maintain the temperature and you added particles, what would that do to the volume? Make it go up proportionally. Or if you remove particles, it would make the volume go down proportionally. Okay? So Avogadro, along with the French dude, that I won't mention his name, okay, came up with this idea called molar volume. Now, this is a very important. This is only the case under those specific conditions. Could I come up with a different number of different conditions? Yes, but why don't we just focus on one condition? Okay, so you don't have to memorize a whole bunch of stuff. What this says is that the moles are so closely related to the volume. Okay, guys, and the reason why this is, because this isn't, what I'm about to say isn't 100% true, but it's enough of a good enough of an approximation that we use it all the time. Okay, what they're saying with this, they're saying that any mole of gas, nitrogen gas, oxygen gas, chlorine gas, fluorine gas, any kind of gas, if you have a mole of particles, they all occupy the same volume. So if I have a mole of H2 gas, how much volume will it occupy? 22.4 liters. If I have a mole of carbon dioxide gas, how much volume will it occupy? 22.4. If I got a mole of you name whatever gas, how much volume does it occupy? And the reason why they approximately occupy the same amount of space is because most of a gas is open space.
Is it approximately or exact?
It's approximate. Okay, and I want to show you.
So all gases the same?
For volume, it's very similar. Let me have you open up your book to a page.
Or is gas?
Page. Where is it? Page 265. Everybody get there, please, for me. Okay, there's a data table on 265. No way you're there, Trinity. Everybody see the data table? Okay, in the left column you've got the gas, in the far right column you have your molar volume. Look at those numbers closely.
They're all like the same.
They're all pretty close to what? 22.4. But are they all perfectly 22.4? Okay, and really the difference in their volumes has to do with the size of the particle themselves. But remember, since the particle itself takes up so little of the overall volume of a gas, we can assume that it's essentially negligible. We can almost assume that the gas particle itself occupies no volume. Now, we know that's not true, right? But because, like, if this was my gas, if this is my gas molecule, and the rest of this room is the space that it occupies, are you gonna, like, when you measure the volume of this gas, are you gonna be worried about this small little volume here? Is that gonna really affect the whole volume that it occupies? It's not. So whether I've got hydrogen gas, which occupies very little volume, or maybe like chlorine gas, which occupies a little bit more volume, do you see how, yes, they have different volumes of particles, but compared to the whole open space that it has, it's nothing. That's nothing. Does that make sense? Okay, so what we can do then is, instead of knowing every little standard volume number here, we can make an approximation. Okay? Because if we do that, it makes the math easier. We don't have to look at a data table every time, and we can say, well, it's close enough to 22.4, you know, good enough for government work. Right? So, with all that being said then, we can use this as a conversion factor when I'm converting from moles to liters or liters to moles only when what?
Needs those.
Yes, when you're at STP. You cannot use that at STP. Does that mean that the ratio isn't relatable? No, the ratio is still held constant, but it would be a different number. Okay? And since we know STP fairly well, what is STP?
1 atmosphere and
273 Kelvin, 1 atmosphere of pressure. Okay? So, come on. Let's do something like this. Okay? It says, what volume will 4 moles of ammonia occupy at STP? Okay? Well, you might know what ammonia is?
NH4.
Nope. What?
No, wait.
NH3.
NH3. Dang it. Ammonium ion is where you get NH4.
Dang it.
So if you give a number of hydrogen to ammonia, you get an ammonium ion. All right. Now, since it's at STP, I know 1 mole has a certain volume. So if I have 4 moles, it will be 4 times that volume.
2.4.
Okay? 1 mole occupies 22.4. Now, is that 100? If I were to look up in the book what the molar volume of ammonium is it going to be exactly 22.4?
Yeah.
No. But is it going to be close enough for?
Government work.
Yeah.
Yeah.
Okay? So when you do this, you should get what? 90 what? 89.6. Close. Yep, 3 sig figs. And that's the volume it occupies. If I gave you, and I said a certain gas occupies 23.99, that's probably not a good example. If I gave you a gas that occupied 50 liters at STP, could you tell me how many particles it had?
50 times 6.02.
50 liters times the molar Avogadro's number? No, you can use this idea that I know that if I have 22.4, it's 1 mole. So if I had 50, it would be what, a little bit more than 2 moles? And then you can figure out from there how many particles that would be using Avogadro's number. You see that there's some pretty practical uses of that. I can just measure the volume of a gas and pretty much know how many particles it has within a close estimate. Neato.
What about chlorine 2? It's only like 22.
22?
0.1.
Yeah, it's different. It's off by, but that's also your highest molar mass guy, so it's going to take up more of the volume. So, all right, let's do this one. A little bit more difficult than simply just using Avogadro's law or the molar volume. Okay, so this 1 mole equals 22.4 is called the molar volume. Okay, that should be pretty easy to remember because 1 mole equals this much volume. Molar volume. Okay? Similar to how we did molar mass, was how much mass was in a mole. Make sense? So, let's tackle this one. Now, this is missing some, oh yeah, there it is. Okay. Do you have this part in your notes? Is that there? Okay, because it's not in mine, so I think I must have put it in because it needed that information. Okay? So it says, what volume will 2.50 moles of hydrogen gas occupy at 300 Kelvin and 400 torr if we assume my initial conditions were at STP? What do you think we should do?
You're gonna have to find the difference in volume from STP to 300 Kelvin 4 and 4 first. Alright.
Well, we're just trying to find the volume. So if we knew the difference, we'd already know the volume, wouldn't we? So, question is, how are we going to find volume?
We're gonna use one of the equations that we have already. And
Any ideas which one?
In this case, it's gonna be the last one, I forget what it's
Combined
called.
gas.
Combined gas law. Pretty good.
And STP, so we know what we achieved in the second one.
So we said our initial conditions are at STP, so does that mean I could say T1 is 273? And I could say P1 is, I'm going to need it in torr. What is it in torr?
760.
760?
Yeah, I meant the difference in moles, not moisture.
Okay? Now, we don't know V1 technically, do we? Can we figure it out?
Yes, 2.5
It's
times 2.4.
2.5 moles, because right, we're at STP here, so I can figure out exactly the volume that I need. Anybody got a number? 56. Second to that, everyone, someone give me a.
It's 56.
Yep, okay. Then it gave us P2 and T2. Can you find P2? Go ahead.
Take my calculator right here. Let's see if we'll get it.
What? Why is P? Because it's standard temperature and pressure. We know standard pressure is 1 atmosphere, which is the same as 760 torr. Right, does that make sense? Like you remember we had that big long equal expression that said 1 atmosphere equals this, equals this, equals this. Okay, so if we know standard pressure is 1 atmosphere, we can just convert it to our torr unit that's equivalent. Good question. Everybody understand why we got these numbers the way we did? Okay. What'd you get? Are you still working?
117.
117? Amen to everybody?
Amen.
Any questions? Quinn, did you get that?
My calculator won't let me do it.
Calculator won't- You're gonna want to get a calculator that can let you do it then.
Yeah, well, it just, when I try and do it, it just gives me a reduced fraction, so that's.
Oh, I gotta figure out how to get to the. Can't you reduce that in your head? Why don't you do like, long division? Can't you do that? That's not gonna be me. She's looking at me like, you. Okay, I will. Okay, 117, good. You know what's also cool about this?
You can find
Density, that's standard temperature.
Okay, because there's a relationship between molar volume and molar mass, which is really nice. Because what you then can do is if you know the density of something and you know what its volume is, you can measure its volume pretty easily. You can measure its density pretty easily because you would just figure out what it weighs, you would figure out what its volume is, and you would have your density. Mass divided by volume. What's cool about this is if you have some unknown liquid or gas, probably gas in this case because we're dealing with molar volume, if you had some unknown volume, you could weigh its mass, you could find out what its volume is, and from that information alone, you could identify the molar mass of an unknown gas. So, if I were to change this equation, it kind of is goofy. I don't know why they choose G as your molar mass variable. It's kind of goofy to me. Wouldn't you say? No, don't care. Good. All right. That's awesome. Density is I'll just do big M little m for molar mass and big M little v for molar volume. Okay? Now, what's the problem? What is the density of hydrogen gas at STP? And why does it have to be at STP?
Because we don't know any other number for anything else besides this.
Okay, so what would at STP tell us?
273 and 1.
Yeah, but we don't need any of those two things for this equation. What does that give us up here?
It gives us that hydrogen's going to be added to grams, and the bottom denominator is going to be whatever.
Well, however
44.2.
many moles.
Yes,
Sorry, 2.4.
yes. The fact that it's STP tells us that that is 22.4.
And you know it's 1 mole.
What?
Shouldn't have to be 1 mole.
Sure.
You can just put.
But that's what you're doing when you're finding molar mass. It's per 1 mole. So, I know I didn't quite derive the equation for you, which it may have helped if I drove the equation for you, but usually that just derived the equation for you. But usually, students just snooze while I derive equations and they don't think it's that interesting. So I tend to not. So, what is the density? Density equals molar mass. Do we know the molar mass of hydrogen gas? Nope.
2.02.
Oh,
That's
dang,
right.
I knew that.
And do we know the molar volume if we're at STP?
2.4.
Everybody see how the moles are going to cancel there? Leaving us with the units per density, a grams per liter, a mass divided by a volume. That's neato. What'd you get? 0.0902. Yep. Alright, I want you guys to do the next two. Where's your hammering? I'm done. Once you get the answer to the second one, you'll probably kick me. Wait.
I'll keep this for
Did you find out why I said that?
I'm kidding.
Trinity's confused. Trinity answered the second one?
Which second?
And you round that, what do you get? Round that to 4 sig bigs, or to 3
I
sig
just
bigs.
found that
Maybe
in
like
the book.
420 or something.
I don't know how to do that.
No.
Kramer.
Okay.
I just got that out of the book. I don't know what that's supposed to be.
You don't know what the molar mass of oxygen gas is? And it gave you the density. So solve for molar volume. But guys, if we're solving for molar volume, what should we assume it's pretty darn close to?
22.4.
22.4.
So, there you go.
What is this answer?
That's not the molar mass of hydrogen, oxygen gas.
Is that right
That's the molar mass of hydrogen.
16.
It's actually 32,
What?
but
there? Well, I did 32.
Oh,
And I got this.
Oh my.
you should. Your 32 divided by 1.429.
Wait. So confused.
All right, I don't know why we're so confused. I'll show you how to do
I
it.
have. I just plugged in my calculator and got
.0446.
If you ever use this equation to find molar volume, you could just assume it's 22.4 because what is molar volume? 22.4. Now, it may not give you perfectly 22.4, and it shouldn't. So in this particular situation, we have the densities right there. 1.429 grams per liter, not milliliter.
Alas,
Okay.
I did divide it.
We've got the molar mass of oxygen gas. What is it? 32, because oxygen gas is diatomic. Can you solve for molar volume or variable x?
She needs a golden calculator to divide.
What the heck?
Is that a song?
It's talking about this girl that's like, it's called Roses. It's like this girl that looks really like pretty or whatever, but she's actually just like a terrible person. She's really down.
Like when you try to buy something at the store that's $29.33, and she looks around for the calculator for an hour.
I don't know.
I did that once. Did I ever tell you that story? I went and bought something at the Nike store that was $29.33. I handed this cashier, this lady, this girl who was probably 22, and she started wandering around aimlessly, and I'm just like, what is she doing? And I was like, what's going on? I can't find my calculator. She couldn't make change. In her head.
See, but no, when I'm
The
taking
chorus?
money all
Did you
day,
hear the chorus that's on
Kramer, that's not fair, because when I'm taking money all day into with so many numbers, I cannot, like, at the end of the day, I cannot do a simple.
Don't be a teacher then.
It says the chorus.
You'd be a bad teacher.
This is the chorus. It says,
Honestly, you'd make the
"Those
worst
just
kind
really
of
smell
Thank
like."
you,
Oh my
Rose.
gosh, you're so smart. Miss Natalie, how could you get this wrong?
So that's hard to do that's hard to not do as a teacher. I'm telling you that now.
Yeah.
I believe it.
It's very difficult.
It's hard not to
Stop
big
myself.
brother. Every time I come in the morning, you're like,
Isaac, smile.
no comment.
I got one wrong.